number theory, you study divisibility a lot. And one of the reasons for this is a result we call the fundamental theorem of arithmetic. Basically, this says that every positive integer greater than 1 can be factored into a product of prime numbers in a unique way. For example, 6 is 2 times 3, 10 is 2 times 5, 17 is prime, so it's just 17. You can't break it up into smaller prime numbers. And when we say that an integer can be factored in a unique way, we have to be a little bit careful here. For example, look at 12. 12 is 2 times 2 times 3. Now, someone else might write it as 2 times 3 times 2, or maybe 3 times 2 times 2. These all give the same thing, so you'll often hear the phrase unique up to order. What that means is if you don't worry about the order of the primes, then the factorization into prime numbers is unique. With that in mind, it's kind of natural to say, okay, let's start looking at these integers to see if there's any pattern to them. You have some numbers like 13, prime numbers, where the only divisors are 1 in itself. In fact, that's one way you could define a prime number, an integer that's only divisible by 1 in itself. There are other ways to define prime numbers. By the way, there's one exception to this definition. We don't consider 1 to be a prime number. It's not a prime even though it's divisible by 1 in itself. We call 1 a unit, and we'll explore that later. So we have prime numbers like 13. Then you have numbers like 24. It's not prime. It can be factored as 2 times 2 times 2 times 3. Because it's not prime, we call it composite. Now, if we were to look at the numbers that divide 24, there's quite a few of them. There's 1, 2, 3, 4, 6, 8, 12, and 24. So it has 8 divisors. A divisor is a number that divides another number evenly. Literally 1/3 of the integers from 1 to 24 divided evenly. So with that in mind, what we would like to do today is explore how divisible an integer is. And to do that, we're going to be using certain terms and notations frequently. So let's go ahead and talk about those. We say if x divides y evenly, then x is a divisor of y, and we write it like this. For example, 3 is a divisor of 12, and 5 is a divisor of 25. Now, 7 is not a divisor of 40, so in that case, you put a little slash through the vertical line to indicate that it is not a divisor. So how can we measure how divisible an integer is? In number theory, the way you do this is you use a function that kind of counts or quantifies integers based on their divisors. These kinds of functions are often called number theoretic functions. You might even hear the phrase arithmetic functions. One common number theoretic function is the sigma function, which is also called the divisor function. It's defined to be the sum of all integers that divide an integer. For example, sigma of 8 would be 1 plus 2 plus 4 plus 8, which is 15. Another arithmetic function is the tau function. This is the number of divisors, not the sum of the divisors, but just the number of divisors. For example, tau of 8 is 4, because there are 4 divisors, 1, 2, 4, and 8. Tau of 12 would be 6, because there are 6 divisors, 1, 2, 3, 4, 6, and 12. And tau of any prime number, p, is 2, because the only integers that divide a prime number are 1 in itself, p. For historical reasons, we're going to focus on a third function, s of n. This is the sum of all proper divisors of the integer n. A proper divisor is an integer less than n that divides n, so it's any divisor other than n. We'll start with 2. S of 2 equals 1, because if you look at the proper divisors of 2, there's just 1. Remember, we're not counting the number itself. S of 3 is also 1. S of 4 is 1 plus 2, which is 3. S of 5 is 1. Notice that S of p is 1 for any prime number p. S of 6 is 1 plus 2 plus 3, which is equal to 6. S of 7 is 1. S of 8 is 1 plus 2 plus 4, which is 7. And we can continue. Now, in ancient times, when Euclid was around, there was this tendency towards numerology. People thought there was a mystical importance to some numbers, and they noticed that there was something special about the number 6. The sum of its proper divisors was 6, and then they looked at 28, and the sum of its proper divisors, 1, 2, 4, 7, 14, is also 28. And the numbers 6 and 28 are important to people for other reasons. For example, it was believed the universe was created in 6 days, and 28 is roughly the number of days it takes the moon to orbit the Earth. They put a lot of significance on those numbers. They called those perfect numbers. So people broke all the integers up into 3 different categories. If the sum of the proper divisors is less than the number, we call it a deficient number. If the sum of the proper divisors is larger than the number, we call it an abundant number. And if the sum of the proper divisors is equal to the number itself, we call it a perfect number. This raises a few interesting questions. One is, how many integers are there in each of these 3 categories? Is there an infinite number? We can actually jump in and answer some of these really quickly. Deficient numbers are straightforward because for any prime number p, s of p equals 1. So prime numbers are all deficient. Since there's an infinite number of primes, we know there's an infinite number of deficient numbers. What about abundant numbers? We have 12, that's an abundant number, and here are the first few abundant numbers. One pattern is if you take any power of 2 greater than 1 and multiply it by 3, then that number is going to be an abundant number. We can quickly show why this works. If you look at the proper divisors of 2 to the nth times 3, you have 1, 2, 2 squared, on and on up to 2 to the nth. And then you have 3, 2 times 3, 2 squared times 3, on and on up to 2 to the nth minus 1 times 3. Remember, we're leaving out 2 to the nth times 3 because that's not a proper divisor. And if you add up all these divisors, which are 2 geometric series, you get this expression. When simplified, it's abundant whenever n is greater than 1. So there's also an infinite number of abundant numbers too. This isn't all of them, but it is an infinite number of them. That leaves the perfect numbers. We know 6 is perfect and 28 is perfect, and the next 2 perfect numbers are 496 and 8128. Those were the only perfect numbers known thousands of years ago. They did notice the last digits of these perfect numbers alternated between 6, 8, 6, 8. Also of these 4, the first one has 1 digit, the next one has 2 digits, the third has 3 digits, and the fourth has 4 digits. So they thought that was the pattern, that for any number of digits, there was one and only one perfect number, and the last digit alternates between 6 and 8. Unfortunately, it turns out this pattern breaks down pretty quickly because the 5th perfect number is 33,550,336. It does end in 6, but it does not have 5 digits. But it was a pretty good guess based on just 4 examples. This also brings us to an interesting spot. We're just about to the point where no one knows much more than what we've already seen here. We know there's an infinite number of abundant numbers and an infinite number of deficient numbers. But what about perfect numbers? People think there's an infinite number, but we don't know. Also, if you look at the first few perfect numbers, you'll notice a pattern. An easy one is they're all even, but there are other patterns too if you dig in and factor them. Each perfect number is a power of 2 times a single prime. But this prime number isn't just random, it's actually one less than another power of 2. And in fact, it's 1 less than 2 to the power of a prime number. If we go back to the time of Euclid, he showed that numbers of this form are perfect if the second part is a prime number. Euler showed that this is true of all even perfect numbers. If an integer is perfect and it's even, then it must take this form. And this prime number here we call a Mersenne prime. So for every Mersenne prime you get a perfect number, and every even perfect number corresponds to a Mersenne prime. So this brings up the question, is there an infinite number of Mersenne primes? We don't know. All these examples of perfect numbers are even integers, which raises another question. What about odd integers? Is there an odd perfect number? Well, we don't know that either. People have worked on it and have been able to make a little bit of progress and show that if there is an odd perfect number, then it has to have this property or that property, and this whittles down the possibilities. So that's where things are today.